Okay, so in this second half, I want to deal with some of the equations of a simple harmonic oscillator, and to kind of keep it a little interesting for this level of course, I'm going to do it via the Lagrangian approach, but just so I can do it for context, I'm going to do it via the Newtonian approach at first, because that actually ends up being easier for such a simple system. Let's draw up our system here. We have some fixed point that we connect a spring to, and that spring has a spring force K, and then we have some frictionless surface here, and we have some mass sitting on that surface M that's connected to that spring. And you can imagine there's some equilibrium position XE, which would be where the mass on the spring would sit if there was no forces and no motion involved. And then you can imagine this is then some position X out here, which is going to vary as a function of time as this system oscillates backwards and forwards, okay? So the force here is just Hooke's law, and we've all seen it many times before. It's kind of one of the first things you learn when you do physics. F is equal to minus K times the displacement from the equilibrium position, X minus XE. And of course, the usual thing that you do, just as a convenience, is set XE equal to 0. And if you do that, then you're just dealing with minus KX, okay? But the more general expression is to have X minus XE, just because sometimes you need to keep that in as a term. And bear in mind, the same argument with the Lagrangian holds in here as well. That XE would go away because when you take dl on dx, your kx part would stay because x is a variable, but xe is a constant, so you take the derivative would take that out, and so automatically you can see that that's not going to matter in the Lagrangian root. It's just an accessory. Okay. We also have our potential energy in here, and we'll deal with that in a moment. So the normal Newtonian approach is you make the total force equal to the balance of all the forces. In this case, there's 1, and then you make that equal to mass times acceleration via Newton's second law, okay? So the Newtonian approach here would mean we can get to our equation of motion almost directly. F is equal to minus kx, and that's equal to mx double dot. And of course we can pull this out. Mx double dot plus kx is equal to 0, and this would be our equation of motion, okay? Very, very easy thing to do in Newtonian mechanics, and it's the main reason why we do it that way, because it's the easiest approach. If you were doing your Lagrangian approach, there's a few steps to it. And that makes it harder in this case, but a lot of the easy problems, the Lagrangian approach is harder and it's not worth the effort. The first thing we need to do is get the potential energy, right? And we know that F is minus dV on dx. So V will be minus the integral of F dx. And so here we have a half kx squared plus a constant just in here, okay? And of course the two minus signs cancel each other out in this particular position. And again, this constant is one of those things that when you take the derivative, it's going to disappear, so we don't really need to worry about it very much. We also in here have the kinetic energy, and so it's going to be a half mv squared. And of course, this time the only thing that matters is the motion along x, right? So this thing's really easy to write. It's a half kx, sorry, not half kx, half mx. Half mx squared, okay? And I'll apologise right now for the leafblower noise in the background. I've been fighting it all day, and there's I'll see if I can engineer it out of the recording, but some people insist on using tools that just scatter things everywhere when the easier solution is just to use a broom or a rake. I don't know, I don't get it. I never intend to own a leaf blower. So now we write our Lagrangian. Lagrangian L is equal to T minus V, and so it ends up being a half mx dot squared minus a half kx squared, just in here, okay? The next step in here is we would write the Euler-Lagrange equations, right? And so what we would have is d on dt of dl on dx dot minus dl on dx is equal to 0. And so we need to get these two derivatives, right? So dl on dx dot is going to be the 2 will cancel the half, and so we end up with mx dot, and of course the x terms don't count there. And then if we're taking d on dt of that, this thing's going to be mx double dot. And of course, we don't need to take the time derivative of m because it's a constant. dl on dx is then the square pops down in our and kills the half in our kx term, and so here we're left with minus kx, right? We have to be careful about the sign just in here. Okay, so we can pull this together. We've got this term here, which is this, and then we've got this term here, which is this. And so if we pull this together, mx double dot minus kx is equal to 0. In other words, mx double dot plus kx equals 0. And you can see straight up here that the equation of motion that we got up the top here is the same as the equation of motion we get down the bottom here from Lagrange's approach. It's just that Lagrange's approach in this particular case takes a little bit more work, okay? At this point, some of you will be going, oh, I'm feeling a bit gypped because this Lagrange's approach just gets me the same answers for a little bit more work. But later on, when we get to lectures 8 and 9, we'll see where the real power of this thing comes in solving problems. It's not intended to buy us a quick entry. It's there to buy us a quick exit. And sometimes you need quick exits. Okay, so what we've got here is another ordinary differential equation to solve, right? And you've probably all done this one in first year, so I'll move a little quickly with it. The way you do it is basically just make an inspired guess and validate that guess. And what I'm going to do today is do it as one of those arrangements where I guess an imperfect solution and then use that to make a better guess later. I was listening to a really good set of comments on the weekend where someone said we need to fail better. And this is one place where it really holds with ODEs. Sometimes you need to put a solution in and then fail your way to a better solution, okay? So what we're going to do here is our trial solution is say that x is equal to EQT, okay? Q is just some constant, and we're yet to determine what that is. And some of you will go, why haven't you put a prefactor in the front? And the reason why I haven't put the prefactor in the front is because, let's just say I have good inspiration. I kind of know that I'm going to need more than one later on, and I don't want to set myself up yet to carry a whole pile of baggage only to find out that it's not quite ideal. Okay, so I'm going to play around with this one first, set myself up for the right situation, and in my better solution, the better solution that I fail to, we'll have that term in there, okay? So let's consider this for a moment. We've got mx double dot plus kx equals 0 becomes m d squared on dt squared eqt plus keqt equals 0, just to write it out in full detail, okay? And so I can work my way through and start taking this derivative. So this is going to be md on dt of qeqt plus keqt equals 0. And then we take this derivative again, right? So this is now going to give me a q squared eqt plus keqt equals 0. And then I can collect my terms. So I've got mq squared plus k eqt equals 0. All right, so I now have two separate terms here that I can make go to 0. This exponential is not very useful to make go to 0, and it's not very useful to make go to 0 because the only way I can do it is take the time all the way out to either plus or minus infinity, right, depending on what the sign of q is. So it's not going to get me anything very useful. The other way to go to 0 here is to basically take this prefactor and make it 0. And this is a really common thing, and we do it so often that this equation up front usually has a name. We call it the auxiliary or sometimes the subsidiary equation, depending on which book and which course you're working in, right? So we want to solve this thing. We basically want mq squared plus k equals 0. We can cluster the terms. So q squared is equal to minus k on m. And so you'll already spot here that q is imaginary, right? There's a minus on the other side. Q is equal to plus or minus I root k on m, assuming that k and m are real numbers, and they must be because they're physical quantities. And we can call this thing basically plus or minus I omega naught, where omega naught is square root k on m. And all of you know from first year that omega naught is basically the angular frequency of the oscillations that we have in the system. Okay. All right. So we've got that. But what we know here is there's going to be two solutions, right? There's a plus solution and a minus solution. And so our better trial solution to use in this particular case would be x of t equals c plus e I omega naught t plus c minus e minus I omega naught t. I know you can see why I left those prefactors out earlier, because I kind of needed to see what this was going to look like to make sense and realize actually I need more than one to play this game. Okay, so C plus and C minus can be complex, right? And I'm pointing that out simply because I don't want anyone to make the assumption that they can be real, because if you restrict them to being real, the problem no longer works, okay? And so this is sort of a general rule in physics: try to allow the biggest possible space and restrict it in with information you know, rather than taking assumptions, because things can get dangerous. Okay, so at this point here I need Euler's theorem, right? And you will have all proven this in your first year complex maths courses. Basically you can write something that looks like this: E plus or minus I u equals cos u plus or minus I sine u, like so, okay? I never bother remembering this, and I'll tell you why. I remember something that's associated to it that's actually kind of useful. I tend to remember this thing: E I theta, E minus I theta equals 1. And I call this old MacDonalds Rule in terms of my little mnemonics things. And the reason why I call it old MacDonalds Rule is I go, old MacDonald had a 1, E-I-E-I-O. And so when I say that, I say old MacDonald had a 1, E-I-E-I-O. And I know just visually the O is a theta, and then there's a minus sign in there to balance off the two terms. And of course, I can sort of bootstrap this thing out of that by knowing that if I multiply this for the plus sign times the minus sign, I get cos squared theta and sine squared theta, and that is equal to 1. And so I never bother remembering this thing at the top. I just remember the one at the bottom. Whenever I need it, I pull it out. Okay. It's kind of a clever tactic in physics, is rather than try to remember everything, which your brain often doesn't like to do, try to remember the few things that enable you to get to multiple places, because you can then sort of consolidate your knowledge and just have webs out from there that get you the various things you need. Anyway, you can recast this thing up the top here into two forms. Cos u is eiu plus e minus iu on 2, and sine u is eiu minus e minus iu on 2. And of course you can prove for yourself that those match that equation 1 that I put just above, okay? And so what this enables us to do is to take our expression up here for x in terms of e's, which you can see that this is obviously going to be an oscillatory solution because it's ei omega t, and write it actually in terms of cosines, right? So what we would have here is x of t is a cos omega naught t plus b sine omega naught t, okay? And I'll let you convert between the two because you've all done it in quantum mechanics courses, and if you haven't, you should make sure you know how to do it. But basically what you will find out in here is that C plus is equal to a half A minus IB, and C minus is equal to a half A plus IB, and these two numbers obviously complex, and they're complex conjugates. So, you know, if we restricted them earlier to be real, we would have been in a little bit of trouble because the whole thing wouldn't have hung together, okay? I'll let you verify that one for yourself because it's fairly easy. There's one last step that I do want to take in here, which I will spell out in a little bit of detail, which is to make a substitution that looks a little bit like this. A equals A cos phi, and B equals A sine phi, where A is a constant and phi is a constant. And we'll attach a physical meaning to those two things in a moment, right? But first, I just want to look at how this comes together, right? So what we can do is take our x of t from up above, and we can write it with these two terms, big A and big B, in there. So it would be A cos phi cos omega naught t plus A sine phi sine omega naught t. And then we can use this relation here, cos alpha minus beta is cos alpha cos beta plus sine alpha sine beta. And I almost never remember this one, I just look it up. The key thing is to know that it exists and you can use it. That will clean this term up, and it doesn't really matter which order you do this in. So this would be basically A cos omega naught t minus phi. And you can prove for yourself that you could write that difference around the other way and you'd get exactly the same answer out. Okay. And so now we need to relate A, big B, and phi. And so we can do this in the following way. We can write A squared plus B squared. And of course, it will be A cos phi squared plus A sine phi squared, which is just A squared cos squared phi plus sine squared phi. And of course, this thing's 1, so this is just A squared. And so we can write that A is equal to A squared plus B squared, like so. Okay. And then the other one we can do on here, if we wanted to, is write B over A. And then B over A is going to be A sine phi on A cos phi. And the two A's cancel out, so this is just tan phi. And so now we can write phi as inverse tan B on A. So we can take our solution to our differential equation. We can go from this form here to this form here, knowing the complex numbers. Okay, so from this version to this version, and then we can take it to this version using those relationships that we just got for big A, big B, A, and phi. And so now what we can do is take this form here and carry this on forward. But before we do it, I just want to show two graphical relations for what it looks like, okay? And you'll know at the moment that A is our amplitude, and omega naught is our angular frequency, and phi is our phase angle, right? So sure enough, if we draw a graph in here of time and position x, what we're going to get is some cosine wave on here, drawn not perfectly, but all right. And then we'll have just ignore this. Actually, let me just see if I can get it to give me. Let's see, just get rid of that bit. Okay, let's draw it like that. It's a really bad sign, but you get the point. This here would be our amplitude, so this would be A. This would be our minus A down here. This difference here is our phase angle phi, and then of course, as you know, our omega naught is related to our wavelength in this particular system. Okay. Now we have one problem which we'll solve in a minute, which is that we have our amplitude A, but we don't know what it is in terms of physical variables of the system, right? We need to do a little bit more work to solve that out. So this graph you'll have seen in first year quite a lot, right? But I have to put it there for completeness. The one that's more interesting to highlight is that our x of t, which is A cos omega naught t minus phi, you could actually just write this as the real component of A, E, I, omega naught t minus phi. And the reason why this is graphically interesting is that if you think about your complex plane, you got a circle in here with radius A, and actually I shouldn't use big A, I should use little a. Little a. Okay, so this point here is going to be A, E, I, omega naught t minus phi. And if you think about what the real component is, it's really just projection onto this real axis here, and it is A cos omega naught t minus phi. Okay, and so really what's happening here is this oscillatory motion is just a projection of the overall circular motion that you get in your complex plane due to this solution back up the top here. Okay, so in the end, that's how those two things are related. And it's I think it's one of the nice observations of sort of undergraduate physics that often isn't spelled out enough, is that essentially 1D harmonic motion is really just a projection of 2D circular motion. And the best demonstration I've seen for this is you take a turntable for long play records, and you put like a little glow sticker or LED right on the edge. And if you look at it from the top, you'll see that go round and round in circles. It's perfectly fine. And then if you rotate it 90 degrees, or you sit down in the plane of the record, what you see is that LED will actually go like this, right? And you can't tell the difference between me just taking the LED and doing this, or me actually going in circular motion if I get the plane right with respect to the camera. Go in circular motion is more or less identical. Okay, so there's a really nice relationship there between 2D circular motion, 1D harmonic motion, in the sense that 2D circular motion is essentially oscillations in two different axes that are joined by some phase relationship. Okay, so with that done, what I want to do is get the term that's missing, and that is a form for the amplitude. Because once I have that, I can draw energy versus position, and I can draw a velocity phase space diagram, right? And the way to get this argument is done differently in different books, and the way it's done in many books kind of highlights the point I was making about work in the second lecture. So back there I was complaining about work being treated sort of not pedantically so that the sign is unclear. And so what I'm going to do is work through the way you'll see it commonly in books. I'm not sure if Taylor does it this way. I pulled this derivation from the book that I used as a second year, and I'll put the details for that book up later. But a lot of books do it this way. And so I want to point out where it gets you into a problem with that work and sign of work argument, and why I care so much about this thing. Okay, so imagine we have massless body on a surface attached to a spring, same problem we've had. The way this argument goes is that you do work to push it away from the equilibrium point, and that work that you do to push it away from that equilibrium point gets stored as potential energy. Okay, this is the way the books derive it. So let's follow that line of logic. When you push that body away, what you're doing is extending the spring. And so you're applying a force in the opposite direction to the force that Hooke's law would apply, right? So what you would have is an external force here that's equal to minus f of x. And of course, that would then be kx in here, okay? And what we do is we work out the amount of work done by that force on the object, okay? So the argument runs like this: wx is equal to integral from 0 to x of the external force dx. And of course, that thing is integral x0 of kx dx. The integral of this is kx squared, and we've got to run that between limits of x and 0, and of course we get out our half kx squared, okay? And then what we do here is we go, okay, well, the work we've done on this thing gets put into the potential energy. So the potential energy now at the position x is going to be equal to a half kx squared, okay? Perfectly logical, perfectly okay. Except that if you go back and think about our work, work kinetic energy theorem from lecture 2, what we said was that our change in potential energy, which is our final position Vx minus our initial position V0, okay, and of course the potential energy is 0 at 0, so this thing is really just Vx. Is equal to minus the work, right? And if we think about that, the work that we just got was a half kx squared, and all of a sudden we're making our potential here a half kx squared and not minus a half kx squared. So we kind of have a problem here, right? There's something funny going on with the signs. And this is what I mean by needing to be really careful about the way this argument runs. I actually prefer to think about the trap that's happening here is you're thinking about the work done by a force that is not the same force as the potential that you're working on, okay? So what's really happening is that the potential energy is the force that's corresponding to the spring pulling back, and you're not working out the work from it, you're working out the work from a force that's counteracting that force, right? And this is where this sign problem coming from. So in my mind, I always like to think in terms of the work done only on forces related to actual potentials in the problem, right? This is the way to get yourself out of this mess. So my alternate parallel stream to this would be actually to think about the work done by the spring force while you push it back, okay? And that's going to be a negative work, right? So let's think about this. It's going to be the work done, Wx, is going to be the integral from 0 to x of the force f of x dx. And of course, this thing is the integral from x to 0. The force fx is actually minus kx, right? It's trying to restore, so it's minus kx in here dx. This will give you minus a half kx squared x 0. And that gives you minus a half kx squared. And then, of course, you use your work KE theorem to go, change of potential energy is going to be Vx minus V naught. We know that V naught is 0. Potential energy at equilibrium is 0 in this case. We just set it to be, so this is V of x. And this is equal to minus the work. Minus the work is minus times minus a half kx squared, which is just a half kx squared, right? And so this is V of x. And so we've got this without any fudges in signs, okay? Only a few of you would have had me as a first year lecturer in Phys 1B now, but the electrostatics chapter in, what is that, Halliday and Resnick, is really terrible for this. They sort of do sign fudges all over the place trying to clean up the fact that they're tying things to forces that are not actually forces connected to potentials, and not making it clear to the student what is going on with the way you have to think, okay? So the optimum way to think about this is to work on the work that's connected to the force that's connected to the potential. If you work on the work on other forces and try to connect them to potentials, things go bad, okay? All right, so with that sorted out, what we want to do here is, you remember when we did the pendulum problem, we dealt with the total energy first, and then we dealt with the Lagrangian. Well, we didn't. We'll do that in a later lecture, but we would have. Here what we did with a simple harmonic version is we work with the Lagrangian, now we've got to deal with the total energy. So the other half of the problem here is to deal with the total energy. Total energy E, of course, is T plus V, and so we can write this thing as a half m x dot squared plus a half k x squared. Okay, so just taking my known terms for these two things. And what I'm going to do here is solve for x dot, right? Because ultimately big E is a constant, m and k are constants, and I'd like to know what x dot is with respect to x, which is the position in my system, okay? So I can solve for x dot, and this will give me a half mx dot squared is equal to E minus a half kx squared. I can get rid of the half here, so this will give me mx dot squared is 2E minus kx squared. I can get rid of the m as well, so this will give me x dot squared is 2E minus kx squared on m. And then I have to take the square root in here, okay? So this will be x dot is equal to plus or minus is always important, 2E minus kx squared on m. And of course, x dot is dx on dt, right? Okay, so what I'm going to do here is try to get time as a variable. And I'm going to do it because it's going to pop me out the amplitude, right? I kind of just know where I'm going with the problem. And again, this is one of these good reasons to do lots of problems, because you kind of get familiar with where things go. So what I can do is write this as dt is equal to plus or minus square root. I have to invert this now, so this is m on 2e minus kx squared dx. And then I can integrate to get t, right? So t is going to be plus or minus the integral of m on 2e minus kx squared dx. What I can do is split this square root here. So put this one on top, put this one in here on the bottom, and I can multiply this by 1 on root k over 1 on root k, right? So really what I'm doing is just multiplying it by 1. And so this allows me to pull a root m over k out the front. So this k here goes underneath that guy, they tag together and go out the front. And then in here I have dx on square root 2e on k minus x squared, okay? Now, so let me just point out what's going on here. This k has gone in here, knocked out that k, joined onto there, and cleaned me up the equation a little bit. Those that have done lots of problems will spot what I'm trying to do here. I've spotted a few moves ahead that this is going to be the kind of thing I'm going to find in a table of standard integrals, and so what I need to do is make it look like a standard integral in order to apply the table, right? And so the one I'm going to get from a table of integrals is going to be integral of dx on a squared minus x squared is minus cos minus 1 x on a plus c C is just a constant, where A is greater than 0, okay? Highly recommend you having a good place to keep tables of integrals. You don't need to remember them. It's just useful to remember what kind of things you tend to find in those tables, because like it's kind of like being in a building, you need to escape the bit. Actually, aeroplane's a good example. When they do the safety demonstration in an aeroplane, they remind you where all the exits are, right? So that if you ever have to leave the plane, you know which is your nearest exit. It's sort of a similar situation with maths and tables of integrals. What you want to know is what, when you're in a really difficult mathematical problem, there's emergency exits, which is to consult tables of integrals, because then you don't have to do an integral, you can just go direct to the solution. And it's useful to know where your best options are for doing that in terms of the table, okay? All right, so we've got this thing. And so what we're going to do here is actually kind of a little bit of a cunning little rewrite. So we can take our t, and it's now going to be plus or minus square root m over k. And now we can use our tabulated integral to knock out this thing above. So I'm going to do it, but I'm going to keep a, right? And I'm going to keep it for a really good reason here for a second. I'm going to go minus cos minus 1 x on a plus c just here, okay? And the reason why I'm going to resist the temptation to stick my 2e on k into there is I can see the physical meaning of a by looking at this equation, right? My cos minus 1 is only ever going to take arguments that make sense that are between plus 1 and minus 1. And if I'm going to run between plus 1 and minus 1, that corresponds to x over a running between plus 1 and minus 1, which basically means that x can only run between a and minus a. And if we think about that back in terms of this graph up here, running between a and minus a in x is really just, you know, this is my amplitude in here, okay? So what I've actually done here is very cunningly taken what is the a in a table of integrals, which is really just the first kind of constant you can think of, right? This is just telling you that you could plug some constant that's got no dependence on x into that thing, and whatever it is will pop out the other end. And now basically just renamed it as my amplitude, right? Now, if I was doing this as an exam problem, I'd have to have a line in here saying what it is I'm doing for it to make sense. But it's perfectly okay that I can do this. And now I can basically say that a is equal to 2e, square root 2e on k, okay? So now I've got an expression for my amplitude. And of course I can clean this thing up here a little bit. So this would be now minus plus m over k, cos minus 1 x on a plus c. And this might be a different constant now, c0, c1, but I don't really care what that constant is, so I can call it whatever I want. It's not really very relevant. I can even set it to 0 in this particular case, okay? Now, the one thing we know here that's really useful is that our a here is going to go between minus 2e on k and 2e on k. And so now we've got something that we couldn't get earlier on in the mathematics, which is what the amplitude is in terms of physical parameters, right? We know it's now related to the total energy and the spring constant. There's one other thing that we're going to want in here, which is what the maximum velocity is, right? And this is actually not so difficult to get. We can get it at x equals 0. And we get it like this. We know at x equals 0 that the potential energy is 0, and so our term is entirely kinetic energy, and it's kinetic energy containing the maximum velocity, right? So our energy is going to be a half m x dot max squared. And we know also from up here that a squared is equal to 2e on k, and that means that E is equal to a half KA squared, right? So we can write that in here as well, half KA squared. So we can now take these two expressions here, the two halves cancel out, and so our x max squared dot will be equal to k on m a squared, and so x max dot will be square root k on m a, right? And we can take this even one step further if we want. X dot max is equal to square root k over m, and we've got an expression for our a. It's square root 2e on k. The two k's cancel out, and so this thing is square root 2e on m. Okay, and so now we've got two really useful things in here. We've got an expression for our amplitude just here, and we've got an expression for our maximum velocity just here. Okay, all right, so I can take this further and start drawing some plots, but again, it's probably easier for me to show them drawn properly than to scribble them on my OneNote pad. So let's come and look at them. So the first one is to look at the energetics. So here we're plotting a graph of x along this axis, energy along this axis, and I'm using the word energy here because I want to be really clear that it can be energy, any energy I want, not specifically E. And on this graph I can plot three energies. I can plot the total energy E here in red, and so you can see it's a red horizontal line because it's constant at all the positions. I can plot V as a function of x. It's my potential energy, and you can see it's parabolic, so potential energy is 0 at the center of motion, and then potential energy is equal to the total energy at the amplitude, which is where the motion stops and reverses direction. And of course I can plot T as well. My T will be a maximum at the center of motion where the potential energy is 0, where it's shooting through the equilibrium position, and then it drops to 0 out here at A and minus A in this thing, okay? And so you can explain all the dynamics of the system by looking at the balances of energies between kinetic and potential energy. And that's essentially simple harmonic motion in the end. It's just a shuffling of energy between kinetic energy and potential energy as a function of time. So you'll maybe not seen that graph specifically, but seen the thinking behind it before in first year. The graph you probably haven't seen before is what the velocity phase space looks like. And it looks a little different to the pendulum example in a couple of ways, okay? So you'll notice here that the orbits here are elliptical. The orbits in the pendulum case can be non-circular as well. They can be elliptical. It depends on the way you set up the problem and how everything fits together, right? In this particular case, the limits on the motion we know with actual expressions in here, right? So if we go to our position where x dot is 0 and x is a maximum, that's going to be our amplitude A, which is square root 2 E over k, and so that's this position here. And then, of course, if we come to this position here or this position here, we're at the center of motion. Our velocity is a maximum. It's going to be x max dot, and that's 2e over m, right? So that automatically sets the two positions on our ellipse. And our ellipse is basically set, its sort of ratio is set by k and m, okay, the relationship between k and m. The different ellipses here, and there's an infinite number of them, right? We only draw a handful, but there's essentially an infinite number of ellipses in here, is set by the amount of energy. So as you move further and further out here, you've got higher and higher total energy inside your system, okay? Now, the reason why none of the other structure that we showed in the pendulum case earlier appears here is because if you think about my pendulum, it has a freedom of motion that's circular, and it basically allows it to come back onto itself in some sort of periodic way. So what we need to do is take that system and take both the low energy motion and repeat it periodically, and also account for the fact that there's a high energy motion that allows it to skip through that periodic structure, right? If we think about our mass on a spring, there's no way that it can go so far out here that it then jumps onto a new spring out that side, or it goes so far over this way that it jumps onto a new spring over that side, right? So the periodicity is gone. There's no further ellipses further out. There's also no motion that we have to have where it can jump from one to another as part of that. And so the separatricities disappear, the external parts disappear, and the periodic sets of conditions disappear. Basically, all we have is a set of ellipses that go out and out and out and out that correspond to ever greater amounts of energy in our system, working our way out in the dynamics of the system. Okay. I think that's pretty much everything I need to cover today, so I think we'll leave it there. Next lecture, we'll deal with damped oscillators, so we'll look at what happens when we have a system that's allowed to lose energy, both in terms of the dynamics and things like phase velocity phase spaces. And then in the lecture after that, we'll look at systems that can both lose energy and gain energy, and you get some interesting behaviors out of those as well. So I'll see you next time.